Hello everyone. In this lecture I shall discuss the fourth type of contour integral. I can say type 4. Right, this is fourth type of contour integral. Fourth type of contour integral. The speciality of this integral is actually we have did it in type 2 and together this we have did it in our type 3. Now this type 2 and type 3 with additional condition that simple pole on real axis. Okay, this type 2 and type 3 with this additional condition simple pole on real axis makes it type 4, right? So now where as usual fx is a rational function satisfy the degree restriction, the degree of the denominator greater than the numerator by at least 1 unit or by at least 2 unit. If by at least 2 units, then we can apply the ML inequality to bring the integral over the large semicircle is 0, or we may apply the Jordan's lemma in general for degree greater than at least 1 unit, right? Now the first job is to avoid these poles on the real axis. So such poles are avoided by drawing small circles, right? Such poles on real axis, right, can be avoided. Means suppose this is a pole on the real axis, this is a pole, so we just indent a semicircle here, right? Our original semicircle is this, consisting of the upper half. Because there is a pole on the real axis, we avoid it by indenting a semicircle. So now our usual approach in anti-clockwise, but here we move in clockwise, right? So this is avoided by indenting the semicircle here, right? So such poles are avoided by drawing small circles with center at these poles and small radii, right? Finally this radii tends to 0, making this point as a isolated point. So now this method is known as indenting the semicircular contour. As I told that we indent a semicircle around this, right? Or we call this is known as indenting at a point, right? So if you recall the real evaluation of exact evaluation of the improper integral, if it is from minus infinity to infinity, then we make it limit a tends to minus infinity a to 0 fx dx, means here it is minus infinity to 0, then here it is 0 to infinity, making limit b tends to infinity 0 to b. But sometimes this integral may not exist. Individual evaluation of this then this may not exist. However, in view of the Cauchy principal value integral, right? Cauchy principal value, we can say the principal value, right? Principal value of this integral. So this Cauchy principal value of the integral is this, means simultaneously we take limit r tends to infinity minus r to r fx dx. So our contour integration is based on this, right? Our contour integration is based on Cauchy principal value of the integral, principal value, right? We will work in line with this, right? So now before the details of the discussion, let me to introduce myself, Professor S.K. Paikray, currently working as a Professor of Mathematics at Surendra University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let us have our details of the discussion. As I have told, the individual integrals may not exist, right? For example, suppose I take limit 0 to infinity your x dx, right? We evaluated limit b tends to infinity 0 to b x dx. If evaluated, this will give you infinity, right? But if I am considering this principal value like this, right, minus infinity to infinity x dx, it is your 0, right? This exists. So we will work in line with this. Our contour integration is based on this Cauchy principal value of the integral, okay? Now to evaluate such integral, as I have told you, we are indenting a semicircle here. So we need an important result here. if fz has a simple pole at z is equal to a, right, at z is equal to a on the real axis, then we indent a semicircle says C1, right, we indent a semicircle, then here you see we indent a semicircle here. So the original contour is like this, say the original contour is like this, original path here is, you say this is your gamma path, and here suppose this is the real axis, and we have a pole here, we have a pole here, say. So we just jump this pole. How will jump it? By indenting a small circle, here, and similarly as many as poles on the real axis we will jump. Okay, so now this is my path gamma. We move here in anticlockwise sense, and here along the real axis from minus r to r, right, we move on. This here in the small circle we move on. This is my C1, say this is my clockwise here rotation, right, and this, clear. So if fz has a simple pole at z is equal to a on the real axis, then limit r tends to 0 means this circle is very small, means the making this point is just isolated, right. fz dz is pi I times residue z is equal to a fz if taken as counterclockwise orientation, means suppose just this is the point, okay, and we are just avoiding this point, with this small circle here. If we take this is in counterclockwise sense, right, then this will be pi I times, right, this is in counterclockwise orientation. Suppose this is my pole A, and this point is just isolated, okay, this point is just isolated. So now here this is the radius is, say this is my small r, so this is small r, so this is my a minus r, and this will be my a plus r, this interval will be this, okay. Now this pole is a here, we call it, this is here a minus r, and this is a plus r, this point is a plus r, okay, and the pole is at a, the center is at a, and the radius is r, radius of the small circle is here r here, and finally we make r tends to 0 to make this circle very small, making this point a just as an isolated point, okay. So our result, so this is the in view of this result, right, for the result and for application to evaluate integral, evaluate the integral, right. So let us just have a little proof of this theorem, proof of this result, then we'll move forward to some standard examples. Now coming to the discussion, or we can say the proof, right. Since fz has simple pole at z is equal to a, so by Lorentz series, so simple pole at z is equal to a means the Lorentz series expansion of fz, right, contains only one negative term here, negative power of z, p1 z minus a, right, and remaining terms are the positive terms, positive power of z minus a, you say gz here. Now where this gz is analytic at z is equal to a, right, where gz is analytic at z is equal to a, or everywhere in your C2 path, in this is my C1, say suppose this path is my C1, in C1 what is my C1 is z minus a mod is equal to r, right. Suppose I am taking this counterclockwise orientation as usual, right, then what we are getting here, now what is a residue of fz, so residue is this b1 only, this residue is the coefficient of 1 by z minus a. What is my residue? Z is equal to a fz, it is my b1 only, is not it, because it is the coefficient of 1 by z minus a. So now if I am taking this as the path, so here it is in anti-clockwise orientation, so 0 less than, here as usual 0 less than theta less than here pi, but here if I am taking clockwise orientation, so here pi less than theta less than 0, right. So you see I am taking C1 as z minus a mod is equal to r, so we can put put the parametric representation here. Z is equal to Z minus A is equal to R e to the power I theta. So Z is A plus R e to the power I theta 0 less than theta less than pi in counterclockwise orientation. So what is your dz? Dz is Ri e to the power I theta d theta, right? So now what is your integral over C1? So integral over C1 fz dz, right? Integral over C1 fz dz is, your fz is this sum of these two. So this is equal to integral 0 to pi. So now substituting this, we can have our integral over C1 b1 by z minus a plus gz dz. Okay, so this is equal to, I can write, we can split it. So this is integral 0 to pi b1, and z minus a is my r e to the power I theta, and dz is my ri e to the power I theta d theta, right? And accordingly my second integral here will be plus integral over C1 gz dz. Now in view of the ML inequality, it can be made less than some m times your length is pi r, right? And which is consequently tends to 0 as r tends to 0. We are taking r tends to 0. So consequently this second integral tends to 0 here. This integral tends to 0 here. So in view of the first integral, your r e to the power I theta, this cancelled here. So this is b1 taken out. Your I integral of d theta is theta 0 to pi. So this is I b1 pi minus 0. So this is equal to I pi b1. What is b1? b1 is my residue. So that is equal to pi I into residue z is equal to a fz. Okay, so integral over C1 fz dz is this. Fz dz is this. Here we have taken the orientation as counterclockwise. Now if you take the orientation as clockwise, and this will be integral C1 fz dz is minus pi I into residue z is equal to a fz, because here the limit of integration, actually this is our need, and here because you are taking the limit is pi less than theta less than 0. The rotation is clockwise rotations, right? So now let us apply this. Now here over this path, right? So over this path we are getting here minus pi I residue z is equal to a f. But over this path, this is integral gamma fz dz. Over this path, it is here 0. It is here 0 because of here, it is in view of here Jordan's lemma in general, right? Or in view of the ML inequality also. ML inequality, if degree of Q greater than degree of P by at least 2 units, by 2 or more, right? Or in general, if it is greater by at least 1 unit, then we apply the Jordan's lemma. You can refer my previous lectures here. Now let us solve 2 examples. So you are asked to evaluate this integral this. Coming to the solution, right? Let my I am taking it from minus infinity to infinity, x4 by x6 minus 1 dx, which is of the form integral c fz dz, right? So now what is my fz? Where my fz is z4th by z6 minus 1. So the poles of fz, this denominator is equal to 0. Here you see the degree is of the denominator is greater than is 2, right? So here poles of fz is what? Poles of fz is z6 minus 1 is equal to 0, 6th root of unity. So this implies z6 is equal to 1. This is here cos 0 plus I sin 0. Because of the periodicity, it is cos 2 pi plus I sin 2 pi. Or I may write it e to the power 2 pi I. Then what is my z? My z is cos 2 pi by 6 plus I sin 2 pi by 6. Or I may write it simply, it is e to the power 2 pi I by 6, or this is my e to the power pi I by 3. If I know this value directly, I may use it this form, or I may leave it this form. Okay, so now I have to find the residue at the, what is my it is I write is 2k pi, right? 2k pi. In general I can write 2k pi, right? It is 2k pi. So what is my k? K is 0, 1, 2, 3, 4, 5. We need these 6 values here, right? 6 number of zeros of this, we should get it, solve it. 6 roots we will get. So now we will check which among them will lie inside, whether the simple poles on the real axis or not. Okay, so now for my k is equal to, 0, what is my z1? Z1 is equal to here cos, so this is my cos pi k, pi k by 6 plus I sin k pi by 6, k pi by 3, it becomes here 3 now. Okay, it becomes here 3 now, it becomes here 3 now. So this is my e to the power I k pi by 3, right? So this is my cos 0 plus I sin 0, cos 0 plus I sin 0. So this is my 1 here. So it is a pole on the, it is on the real axis, right? Then for my k is equal to 1, what is my z2? My z2 is my cos pi by 3 plus I sin pi by 3, right? Here cos 60 is here half, it is here root 3 by 2. So it is 1 plus I root 3 divided by 2 here. It is in the first quadrant, it is plus in the first quadrant inside. Then for here k is equal to 2, what is your z2? It is cos 2k pi by 3, right? 2k pi by 3 plus I sin 2k pi by 3. So this is equal to, you have cos pi minus pi by 3, right? It is not, k is here 2, that's why it is 2 pi by 3 plus I sin pi minus pi by 3. So it is in second quadrant, all sign. So it is here negative here, minus cos pi by 3 plus I sin pi by 3. So this is equal to minus half minus 1 plus I root 3 by 2. It is in second quadrant, minus plus. It is in second quadrant, it is in first quadrant. Okay, so this is inside, this is also inside. Now for k is equal to here, 3. What is your z4? What is your z4 here? So z4 is equal to cos k is equal to 3. So it is cos pi plus I sin pi, cos pi plus I sin pi. Cos pi is minus 1, so this is minus 1. You see, it is on real axis, right? So we are getting 2 poles on real axis, right? Similarly I will get z5 will be the negative of this. I will get the negative of z2. I will get the negative of z2, right? I will get the negative of z2. It will be here minus 1 minus I root 3 by 2. This is in third quadrant, it is outside. And my z6 will be, right, the negative of this. My z6 will be my negative of this. So this will be here 1 minus I root 3 by 2. It is my fourth quadrant, so it lie outside. Okay, so we should now find the residue at these poles. Clearly 4 poles, clearly z1 z2 z3 z4 are the poles inside C. However here minus 1, z1 is equal to minus 1, and here z1 is equal to plus 1 and z4 is equal to minus 1 are simple poles, okay, on real axis, So we have to, so what is my path now? Thus my C is, so what is my C now? Thus this C is now as follows. So my C is, we have the upper half of this semicircle, and at -1 this is my center 0, at -1 I have a pole, at 1 I have a pole. So I have to indent a semicircle here, right? I have to indent a semicircle here, again I have to indent a semicircle here, right? So this is my gamma path, and this is my minus r, radius r however large, and it is in anti-clockwise sense, and here it is in clockwise sense. Okay, here it is in clockwise sense. It is my -1, it is my +1, and it is my 0, right? So now this is my path here. So now by residue theorem, you see, now by residue theorem, what is my I is equal to your integral c fz dz. This c is my whole thing, so it is my this over gamma integral gamma fz dz, right? Then this gamma path is done. Then this point is my -1 minus, suppose I say -1 minus epsilon 1, the small radius is epsilon 1. This point will be -1 plus epsilon 1. This will be my 1 minus, I say suppose epsilon 2. It is my 1 plus epsilon 2. Then it is from minus r to -1 minus epsilon 1. Here it is on the real axis, so fx dx. Then here again over this c2 plus integral over c2 fz dz. This is c1, sorry, this is here c1. So it is c1 fz dz, right? This is c1 fz dz. Then here along this real axis plus up to this integral -1 to epsilon 1, right? Fx dx, sorry, it is -1 plus epsilon 1, -1 plus epsilon 1 to 1 minus epsilon 2, this point to this point on the real axis fx dx. Then it is over the c2 path plus integral over c2, right? It is fz dz. Then we have this to this plus integral 1 plus epsilon 2 to r. It is on the real axis fx dx. Now by residue theorem, integral c fz dz is 2 pi I into sum of the residue at the poles inside C. So these two are on the real axis now. Now two more are inside. Okay, now two more are inside. One is here and one is here. So two more are inside. One is here and one is here, right? So these two will be in the right hand side. It is my, say suppose r1, it is my, say r2 residues. Okay, so now I will find here it is my this c1 fz dz is in view of my result 1, and this is my c2 in view of this. It should be my minus pi I into residue z is equal to -1 fz, and this integral will be my minus pi I residue z is equal to 1 fz. Okay, and this integral will be my 0. It is because of my Jordan's lemma, or since the degree is here 2, or you may apply the ML inequality. So it is 0. No need to write, just you write because of this Jordan's lemma. Right, now in view of this I am taking r tends to 0 here, and I am taking epsilon 1, sorry, r tends to infinity, epsilon 1 tends to 0 and epsilon 2 tends to 0. Then what will happen here? So this integral I becomes, right? So this implies my I becomes here, it is here 0 plus it is minus infinity to -1, right? And plus it is f, and plus it is my minus pi I, right? This integral will be here minus pi I residue z is equal to -1 fz, then plus plus this will be minus 1 to plus 1 f dx, right? This is dx. Then here this will be here minus pi I residue z is equal to 1 f. Then here this, then here integral 1 to infinity f dx, right? So minus infinity to minus 1, minus 1 to 1, plus 1 to infinity, right? This will together, and in your right hand side it will be 2 pi I. In your right hand side it will be 2 pi I, right? Here r1 plus r2, two remaining poles are inside. So now this integral will combinedly give you, right? This integral will combinedly give you minus infinity to infinity fx dx, right? And this remaining will be 2 pi I into r1 plus r2, right? Plus here pi I into residue z is equal to minus 1 f plus residue z is equal to 1 f. So this is the idea. Okay, so the entire description is this. So now we work out what is the pole here, right? What is this residue here, what is the residue here, what is the residue here, and what is the residue here, and we substitute it. Okay, now let us find the residue. Let this be my equation star. Okay, now we find the residue z is equal to minus 1 fz. So this is equal to my limit z tends to minus 1, z minus minus 1, or I may write it numerator by derivative of the denominator. Numerator is pz by derivative of the denominator q dash z. So this is equal to limit z tends to minus 1, numerator is z fourth, denominator is 6z 5. Okay, so this is limit z tends to minus 1 by 6z, right? 1 by 6z. So this is your minus 1 by 6. So as we see, this is inside and this is your inside, minus 1 is inside, and two more poles, one is here, or I can write for simplicity, I write e to the power pi I by 3, right? And here it is, and here it is, I write e to the power, right? This is my e to the power 2 pi I by 3, or I may write it this, so it becomes e to the power minus of pi I by 3, right? So now accordingly my residue at here plus 1, it is here 1 by 6, and it is here at this r1 is 1 by 6z, so it is e to the power minus pi I by 3, and here it is at 2 pi I by 3. Okay, it is e to the power minus this, and accordingly as we see it is 1 by 6 into this, right? So now we add it. Now from star, okay, your integral minus infinity to infinity fx dx is equal to 2 pi I into your r1, 6 can be taken out, your r1 is e to the power minus pi I by 3, and it is here e to the power pi I by 3, and plus pi I times, and here it is here minus 1 by 6, and here it is here 1 by 6, right? Now this and this cancelled here, so this will give you here pi I by 3, it is here cos pi by 3 plus I sin pi by 3 minus I sin, so cos, and here it is again cos pi by 3 plus I sin pi by 3. So it is actually what? It is actually here minus 1 by 6 minus cos pi by 3 plus I sin pi by 3. So it is here minus of, right? So it will here minus of, or you calculate it as your own. So it is minus of this. So it is cos pi by 3 minus I sin pi by 3 and minus cos pi by 3 plus I sin pi by 3. Okay. So here it is cos pi by 3 cancelled. So it is minus, it is pi I by 3 and it is here minus 2i sin pi by 3, right? So here I into I square is minus 1, so minus plus. So it is here 2 pi by 3 and sin pi by 3 is root 3 by 2. So 2 cancelled here. So now it is 3 and root 3 cancelled. It becomes here pi by root 3. So I write it is pi by root 3 or I have pi root 3 by 3 to just match the answer here. So therefore integral 0 to infinity fx dx will be half integral minus infinity to infinity fx dx. So this is equal to half into pi root 3 by 3. Okay, so this is pi root 3 by 6. Okay, or I can write it pi by 2 root 3. Pi by 2 root 3. Okay, so I may write it here pi by 2 root 3. Pi by 2 root 3. I can write it, right? So this is your answer. Okay, so therefore 0 to infinity z fourth by z6 minus 1 dz. Sorry, it is x. So it is here x fourth by x6 minus 1 dx is your pi by 2 root 3. Okay, this is your answer. Now coming to one more example. So coming to this integral, actually here this integral is also called as the psi integral. Okay, sine integral, right? This integral is also known as the sine integral. But actually the sine integral is six is equal to 0 to x sine t by t dt. Okay, so just to compare it, I mention it here, but we are interested in evaluating it. So let my I is equal to integral minus infinity to infinity sin x by x dx. For sin x I write e to the power iz, and for this we write z. So integral c this dz. So now it seems z is equal to 0 is a simple pole on the real axis. So what is my c here? So my c consisting of the upper half of the circle of radius r, however large. This is my path gamma. This is total my c, and it is my 0 here. It is my 0 is a pole here. So this is here is clockwise. If I take this radius as the epsilon, okay, so I can take it. It is my 0 minus epsilon. It is my 0 plus epsilon, because this radius is here my epsilon here, right? This radius here is my epsilon here, right? So now we find the poles of fz. So I write it here. So it is my integral c capital fz dz. So my capital fz is e to the power iz by z, or I can say small fz into e to the power iz. So what are my poles of fz, right? Poles of my fz is same as the pole of fz here. So it is my here z is equal to 0, lies on real axis, right? It lies on real axis, right? So this is my minus r, this is my r, and my r tends to infinity. Now we need to find residue z is equal to 0 fz is equal to limit capital fz is limit z tends to 0 z into here 1 by z here, fz, right? Z into capital fz. So this is equal to limit z tends to 0 z e to the power iz by z. Z cancelled. It is e to the power 0 is your 1. Okay, so therefore residue z is equal to 0. Your fz is your 1 here. So only z is equal to 0 is a simple pole here. If z is equal to 0, lies on z is equal to 0 is a simple pole here. Simple pole, right? And no other pole in upper half plane, right? No other plane in upper half plane. So now by residue theorem, this path is my gamma. So integral c fz dz, okay, integral c fz dz is equal to my integral gamma fz dz plus, so this is my integral gamma, then it is my minus r2 minus epsilon plus minus r2, it is my minus epsilon it is on the real axis fx dx, then over the small path, small circle c1 plus integral over c1 here capital fx dx, then here epsilon to r, then here plus integral epsilon to r, here it is fz, it is the complex path here, it is fz integral c1, it is fz dz, and it is your fx dx. Now taking epsilon tends to 0 and r tends to infinity using Jordan's lemma here. So by Jordan's lemma, this will 0, limit r tends to infinity, integral gamma fz dz is equal to 0. And one more thing, so this is equal to your 2 pi I into sum of the residue. So there is no other residue here, right? No other residue. So this is your 0 here, because no other poles inside, no other pole inside this. So sum of the residue at the poles lies inside. So no other poles here. Let it be my equation star here. So this implies my integral c fz dz is nothing but it is my minus infinity to 0 fx dx, and this integral will be my minus pi I into residue z is equal to 0 capital Fz. So this is minus pi I residue z is equal to 0 capital Fz, and this one will be here plus integral 0 to infinity capital fx dx, and the right hand side is 0 because no other pole inside this. So this is my, now this and this two are merged, it will give you integral minus infinity to infinity fx dx. Okay, now bringing this to right hand side, it will give you pi I into residue z is equal to 0 fz. Okay, so you find it. So now you find it at the right hand side, what is your pole. So that is equal to, you can write, so that is equal to pi I, and we got the residue here. The residue here is residue z is equal to 0, fz is 1, we got it. It is here pi I into 1. So this is your pi I. So what we get, integral minus infinity to infinity sin x by x dx is equal to this. It is actually, now it is here fx here is e to the power ix by x. It is here e to the power ix by x, is not it? You see, it is here e to the power ix by x is here fx, right? So we need, this means I can write it, it is my 0 plus I pi I, right? So now what about my integral minus infinity to infinity sin x by x? It should be my imaginary part of this, imaginary part of 0 plus I pi. So this is my imaginary part, this is equal to my pi, right? This is equal to my pi, but I need my integral 0 to infinity sin x by x dx. So this is equal to half minus infinity to infinity sin x by x dx. So this is equal to my pi by 2. So therefore integral 0 to infinity sin x by x dx is equal to my pi by 2, is not it? So this is proved. Okay, and this integral, as I have told you, it is here psi integral. Okay, sine integral, and it is your sine integral. So in view of that, it is here x is here infinity here, right? The limit is infinity here. So in view of that, I can say it is my si infinity, is not it? So this is my pi by 2. Clear? So we don't bother about that. So this is my integral, and we evaluated it, right? So now to conclude, you can see the series of 4 lectures, type 1 to 4. Okay, apart from that, we have also more integrals involving the multi-valued function, involving the many-valued function, right? Many-valued function. For example, here suppose involving log z, involving z to the power a naught in I, okay, a naught in I, and instead of your semicircular path, we can have your rectangular contour. Okay, rectangular contour. So interested learner can go through this. Okay, now we should conclude here. These 4 types of lectures are the basic and the fundamental. You should focus on that. Many solved examples are solved here, and you should still refer some other examples from any standard books. At this stage, my appeal to all of you is that if you feel this lecture is helpful and interesting, please like and subscribe to my channel. This will boost my motivation to upload subsequent lectures for your benefits. So thank you all. Have a nice day.